Hello, and welcome to the final video in the section on vectors. And in this video, I'm going to go over a few applications of what we've learned about vectors. And this video, I think, is quite nice because it actually ties in vectors to some of the topics that we've looked at previously in the course, some of the topics that a lot of people have questions about. So we're actually going to tie what we've been studying with vectors back to the moment of inertia, which we studied calculating previously when we were talking about double integrals. And then also we're going to connect the amount of work done by a force to line integrals. So these are questions a lot of students have earlier in the course, and now that we've covered vectors, we'll connect what we've studied about vectors back to those topics. Okay, so the first application, really the basis for most of the applications of vectors that we'll consider, is the position of a moving particle, and also the velocity and acceleration of a moving particle. So if we have a particle that's moving as a function of time in space, could be either 3 or 2-dimensional space, its position vector, so the vector from its origin to from the origin to its position, is given by r of t. So we have some vector depending on time giving the position of a moving particle. The velocity then of a particle is the derivative of this position vector. And when we take the derivative of a vector, what we mean is that we differentiate each of the components separately. So dr dt, the derivative of r with respect to t, is just given by differentiating each of the components. And this is the velocity of the moving particle. And then we have the acceleration of the moving particle, which is the second derivative of velocity. We write r with 2 dots over it for the second derivative down here, or we write v velocity with 1 dot. Acceleration is the first derivative of the velocity. And once again, you just differentiate each of the components of the vector separately. Okay, and so when we're studying the motion of particles, we want to know how will a force that's acting on the particle affect its motion. And this is given to us by Newton's law. So this is really the fundamental law of studying the motion of objects or particles. I'm talking about a particle, but we can extend this to objects that are not just a single point particle as well. The total force acting on the particle or object is equal to its mass times its acceleration. So if you divide the force by mass, you get the acceleration, and from that we can determine its motion after we know its initial position and velocity, if we're able to integrate. Okay, so let's look at a fairly straightforward example of this. So suppose we have a particle moving and it's given position vector, and then we want to calculate the acceleration and velocity of the particle, and then also its speed. So I haven't said that on this slide, but remember the speed is the magnitude of the velocity. So let's look at this example. All right, so we have the position of the particle is given by a vector moving in 3 dimensions. The components are t squared times I plus sine of t times j plus 3t times k. So these, remember, I, j, and k are the basis vectors parallel to the x, y, and z axes. Then the velocity is given by the derivative of the position vector. So the velocity vector as a function of time of this motion would be the derivative of the position vector. We just take the derivatives of each of the components separately. So the derivative of t squared is 2t, so 2t times I. The derivative of sine is cosine, so plus cosine of t times j. And the derivative of 3t is 3, so 3 times k. This is the velocity. Now let's also calculate the acceleration, which is the derivative of the velocity. The change in velocity with time. So the acceleration, also a function of time, is the derivative of the velocity, or equivalently the second derivative of the position vector. Here's the velocity vector. You just take the derivative component by component of the velocity vector. So the derivative of 2t is 2. The derivative of cosine is negative sine. And the derivative of 3 is 0, and so there's no k component, no component parallel to the z-axis in the acceleration vector. Right, so this gives the velocity and acceleration vectors for this motion. And the problem also asks you to calculate the speed. So the speed. So speed here would also be a function of time. So this particle is accelerating along its path of motion. Speed isn't constant. And the speed, remember, is the modulus of the velocity vector. And so that will be the square root of the sum of squares of the components of the velocity vector. So 2t squared would be 4t squared plus cosine of t squared plus 3 squared, which would be 9. And so this is the speed as a function of time. Actually, it asks you to say, what is the speed at time t equals 0? So let's finish off the problem by saying at time t equals 0, the speed would be what we get when we plug 0 in for t here. It's the square root of 0 plus 1 plus 9, so that's the square root of 10. So the speed here would be the square root of 10. Of course, we would normally have units, so we haven't specified the units. The position vector would have units of length, meters. Velocity would have units of length divided by time, so usually meters per second if we're working with a metric system. Acceleration, meters divided by time squared, so meters per second squared. And of course the speed is the same units as the velocity. Okay, so this is a simple example illustrating the velocity and acceleration and also the speed of simple motion. Okay. So there's a few other physical quantities that we can talk about when we talk about a particle moving. So suppose the particle has mass m, and it's moving, and the position vector is given as a function of t, r of t. Then the momentum of the particle is another vector, p, usually, and the momentum vector is simply the mass times the velocity. Another way to write the Newton's law, by the way, sometimes it's a little bit simpler this way, is simply that the force equals the derivative of the momentum, as long as the mass isn't changing. Okay, so if the mass is constant, the derivative of the momentum is mass times acceleration, as you can see, and so that would be the force by Newton's law. Sometimes Newton's law is written that way. Okay, another quantity that's of interest when we have a motion which is a rotation, so if we have an object rotating around a given axis, is the angular momentum. And so angular momentum is another vector which is defined here. L is the normal notation, and it's equal to the cross product of r, the position vector, with p, the momentum vector. And of course, remember that the cross product matters which order you do the cross product in, so it is r cross product with p. If you did it in the other order, p cross product with r, you would get a negative sign. Okay, so finally, we can talk about the angular momentum about an axis, when an object is rotating around a given axis. So the angular momentum about an axis is the dot product of the angular momentum with a vector that's parallel to the axis. And so there's an orientation issue as well here. So the vector gives a direction, so that an axis would be a line with a given orientation. So you pick which direction is sort of the positive direction along the line. So you pick which direction is the positive direction along the line, and that's given by a vector. You had a unit vector. And then the angular momentum of the motion of the object about that axis is the angular momentum dot product with that vector giving the axis. All right, so let's look at an example of calculating the angular momentum for a motion. And in this case, the motion is going to be simply a particle of mass m rotating around the z-axis. All right, and so let's go ahead and do that. So let me first draw the situation here. So we have three-dimensional axes. Actually, this particle is rotating in the xy plane, but because I'm talking about angular momentum and using the cross product, we need to think about things in 3 dimensions. And so we have here the x, y, and z axes. And then the motion of the particle is in the xy plane. So note the position vector is always a combination of I and j. So it's in the xy plane, and it's simply moving around a circle of radius r, lowercase r, centered at the z-axis, the origin. So it's rotating around the z-axis on this circle of radius r. And there's another parameter that's called omega, the angular velocity. So that corresponds to how fast it's rotating around. And so the actual position vector for the motion is r cosine of omega t times I plus r sine of omega t times j. All right, so we want to calculate the angular momentum of this rotation about the z-axis. So in order to calculate that, we first calculate the velocity. So the velocity is simply the derivative of r with respect to t. So that's written as r with a dot over it. And you differentiate the components. So the derivative of r cosine of omega t be negative omega r sine of omega t I. And then the second derivative of the second component, the y component, it would be r omega cosine of omega t j. And so this is the velocity. Okay, now the next thing is the momentum, which is simply the mass times the velocity. And the momentum of this motion is p, a function of t, is the mass times the velocity vector, which is equal to, well, this vector multiplied by m, so negative m omega r sine of omega t I plus m, right, in the same order here, m omega r times cosine of omega t j. Okay, now next we'll calculate the angular momentum. The angular momentum and I'm going to remove the slide here in a minute to give myself more room, but let me just remind you what the angular momentum was from the previous slide. So the angular momentum was here, the cross product of the position vector r with the momentum vector p. All right, and so the angular momentum is r cross product with p. So we see r here and the momentum p here. Let's calculate the cross product using this determinant formulation, as I've done in the previous videos. I'm going to give myself lots of space because these components are a bit long, so give myself a lot of space in the columns. All right, and so the I component of r is r cosine of omega t. The j component of the position vector is r sine of omega t. The I component of the momentum is negative m omega r sine of omega t. I see I maybe should have given myself a little bit more room because these formulas are a bit long. And then the momentum, or sorry, the j component of the momentum is m omega r times cosine omega t. And neither of these have a k component, so the k components are 0. Okay, so this is actually easy to calculate the cross product. If you expand along the top row, you would get I times 0 because the determinant here is 0. J also times 0, so there's no I and j component, and then you have k times the determinant here, which is the product of the diagonal entries, is going to be m omega r squared cosine squared omega t plus, or rather minus, the product of the off-diagonal entries. There's a minus sign here, so the other minus we would put cancels out with that minus sign, and we have plus m omega r squared sine squared omega t. All right, and so we can factor out the m omega r squared, which occurs in both of these terms, and we're left with k times m omega r squared cosine squared of omega t plus sine squared of omega t. And cosine squared plus sine squared is equal to 1, as you know, the Pythagorean identity. And so finally the angular momentum is simply k times m omega r squared. Right, so the angular momentum actually ends up being fairly simple, doesn't depend on time anymore, and it is still a vector. And now we want to know the angular momentum about the z-axis. So let me rewrite what we just calculated to be the angular momentum here. We just calculated L was k m omega r squared. Now finally we want to calculate the angular momentum about the z-axis. All right. So remember, let me show you the slide one more time. The angular momentum about the z-axis was the angular momentum dot product with the vector parallel to the z-axis. Now, vector parallel to the z-axis is k, and so the angular momentum about the z-axis is L dot with k, and so this is m omega r squared k dot product with itself. That's the magnitude of k squared, k dot product with itself, which is equal 1. So this is just m omega r squared. This is the angular momentum of this particle as it rotates about the z-axis. And now what I want to point out here is that I should have written this slightly differently as omega times m r squared. And so omega here is like the velocity, it's the angular velocity, so how fast the particle is rotating. And then the mr squared is the moment of inertia. It's like the mass of the rotation here. It's almost like we have velocity times mass, which is momentum. And this mr squared plays the role of the mass, and that's called the moment of inertia. And now, when we were doing double integrals, one of the applications we looked at was calculating the moment of inertia of lamina, so thin plates, using a double integral. And now we can connect this to those calculations. So suppose rather than a single particle rotating around the z-axis, we have an entire plate rotating around the z-axis. So let me try to draw what I mean. Now once again, we have x, y, and z axes. X, Y, Z. And then suppose we have some plate that's here in the XY plane. I'm kind of drawing it as an arbitrary shape, so it's just some shape, but a flat plate in the XY plane. And this is L, the lamina. And suppose you say divide L up into little small bits. So here's a small bit, and let's say this is a small bit with mass delta M. Right? So when we were discussing calculating the mass of plates, these plates with varying density, we discussed how this mass would be the surface density rho times the area element. So the area of that small element times the density per unit area, the surface density. Okay? And so we have the moment of inertia here, mr squared. And we can ask what would be the moment of inertia of this small little bit if it rotates around the z-axis with angular velocity omega. So supposing we're rotating around the z-axis here. So this small bit is rotating around the z-axis. So the angular, or the moment of inertia from that small bit would be delta m times the distance to the origin. So, moment of inertia of this small section is the mass of that section times r squared, its distance to the origin. So r is this distance right here. Okay? Or if we write delta m as the surface density times the area, it would be rho times r squared times the element of area, the area of that small section. Right, and so now in order to find the moment of inertia of this entire plate, we add up the moments of inertia from each of the small little bits. So the moment of inertia of the entire plate, if it rotates around the z-axis with angular velocity omega, well, it doesn't depend on omega, we multiply by omega to get the angular momentum. But the moment of inertia of the entire plate of L would be the double integral over L of the moments of inertia of each of the small bits. When we take delta m, the size of the small masses, or delta a to 0. So rho r squared dA. Right, and this was the formula that we had for moment of inertia when we were doing double integrals. The density times the distance to the axis squared, that's r squared, times dA, double integral over the plate. So this explains this formula that we used when we were calculating these moments of inertia. All right, so that's an application. We're going to look at one other application, and remember at the beginning I said we were going to connect it to line integrals. And so this application is the work done by a force when you move an object a given distance. So from physics, the work done by a force moving an object is the force times the distance. Right? Work is a scalar quantity. If we're working in a metric system, it's in joules, or Newton meters. All right, so this is the formula in one dimension. You've probably seen from mechanics courses in the past. This is the formula for one dimension with a constant force. But really, we want to consider objects moving in 2 or 3 dimensions, not necessarily along straight lines, and where the force might be varying with position. So we want to consider how can we calculate the work done by forces in such situations. So first let's consider just what happens if we have a constant force and we move between 2 points, A and B. Well, the work done is going to be equal to the dot product of the force vector with the displacement vector from A to B, as shown here. Right? So explain why this is. So the reason really is that the work done is the component of F along the direction from A to B times the magnitude of A to B. So this work is the force dot with the vector from A to B. And remember, when we discussed the definition of the dot product, one of the equivalent definitions is this is the magnitude of F times the magnitude of the vector from A to B times the cosine of the angles between them. So we have here A, here B, this is the vector from A to B. We have a force F here. Then this quantity, the dot product of F with A to B, is the component of F in the direction from A to B, which is the length here. Component of F in direction from A to B, which in mathematical terms is the modulus of F times the cosine of theta. I forgot to put theta in this diagram. Theta is the angle between the two vectors. Right. So you take the orthogonal projection of F onto the direction from A to B. That's the component of F in the direction from A to B times the distance from A to B. And the distance from A to B is the modulus from A to B. So distance from A to B is the modulus of the vector from A to B, or magnitude of the vector from A to B. And so this formula is saying that the work done is the projection of F onto the direction from A to B, or I should say the component of F in the direction from A to B, times the distance traveled, the length of the vector from A to B. So this is the explanation for why this is the work when the force is constant. This formula gives the work done by a force field given by F, which is constant, moving a particle from A to B along a straight line. But what if the force isn't constant and we want to move along a curve? Well, in that case, what we do is we divide the curve up into small sections. This is very much like what we do whenever we end up getting an integral. We divide something up into very small pieces, and we consider what would result from each of those small pieces, and then add all those up, and that's the integral. This is what's going to happen here. So we divide the curve up into small pieces, each with displacement vector delta r, as shown, and we approximate the force along this displacement vector delta r as being constant, given by F, and then the work done moving along this small segment of the curve represented by delta r is the force dot product with delta r, delta w, and we add up all the small contributions along the curve, and this results in an integral. In fact, a line integral. So we integrate over the curve C, f dot dr. This delta r turns into dr, and the force is the force along the curve. C is the curve along which a particle moves. And this line integral is the total amount of work. Now, this line integral is given with a notation a little bit different from what we looked at in the past when we were doing line integrals of differential forms, but it's related, really the same thing as these line integrals of differential forms we looked at, and I'll show you how they're related now. So we write for dr, which is the infinitesimal displacement vector, dx times I, that's the change in x times I, plus this infinitesimal change dy in y times j. And then the force field, F, has components P and Q. And P and Q can be functions of x and y, so they can be varying from point to point. Then this dot product of P dot dr is just P dx plus Q dy. And this is exactly the differential form that we integrate. So this f dot dr is actually a differential form, and we see that this work is actually given as this line integral of a differential form, exactly the type that we studied before. So this is the situation. I want to do an example of calculating the work done moving a particle in a field. So here's the example. Really what happens is this just becomes a line integral of the force field along a curve, and we just have to do the line integral. So let's do this. So we want the work, which we call W. It's going to be the line integral along the curve, which is in this case a parabola between the origin and the point 1, 1 of f dot dr, or as I discussed on the previous slide, integral along a curve of a component of f in the x direction, which is just x here, because f is x times I dx plus y dy. Okay, maybe I should put in the intermediate step here. F is x I plus y j, and taking the dot product of dx I plus dy j, and so this gives us the integrand here in this line integral. All right, so now it's a line integral. The curve C is the segment of the parabola, as it says. So along this parabola, curve is y equals squared. Goes from the origin 0, 0 to the point 1, 1. And we can parameterize this parabola using x. So parameterize using x. As the parameter. And so what do we get? We have then that dy equals 2x dx, and so y equals x squared. And so this line integral, giving the work, is the integral as x goes from 0 to 1 of, here this is x dx, plus y, which is x squared, times dy, which is 2x dx. Separate this out. So now we can do this line integral. We combine terms together here. It's the integral from 0 to 1 of x plus 2x cubed dx. And so the indefinite integral is x squared over 2 plus x to the 4th over 2, evaluated between 0 and 1. And so this is 1/2 plus 1/2, or 1, when we add these together, plug in the limits. All right, so this is the total work done moving this particle with this force field. This is the end of the section on vectors. In the next section, we're going to move on and discuss complex numbers, which in a sense are vectors in 2 dimensions in disguise.